Hi, I'm Stu Pinckard. I, along with John Wagner, Will Blackstock, and Kevin Killory, make up Group A46 and Dr. Troy and Dr. Spencer's Biology 1510 class. This is our Module 1 presentation on how plants kick-started evolutionary drama of Earth's oxygenation. Most of our evidence comes from T.W. Dahl's 2010 study regarding the oxygenation of the Earth's atmosphere. We will begin this presentation with John Wagner's introduction.
We know that there was minimal oxygen on the Earth billions of years ago. And as you can see by the graph, there may be even less than 0.1%. Today, the atmosphere consists of 21% of oxygen. The oxygen revolution is the greatest atmospheric pollution event on record. It fundamentally changed the oceanic and atmospheric conditions on Earth. Also, the evolution of life on Earth is directly linked to these changes. We also know about the theory of the Cambrian explosion. This is when, over a short time of about 5 to 10 million years, that a huge number of multi-celled animals with high oxygen demand appeared. This burst of animal forms led to most of the major animal groups that we know today. This proves that the Earth must have evolved to allow for this phenomenon to occur. Next is Stu to talk about the proof of this occurrence.
So we know there was an oxygen revolution, and life as we know it today began evolving from that point. But how do we know for sure when the oxygen really got here? In a study done by T.W. Dahl, 2 molybdenum isotopes were used to determine oxygen levels. These 2 isotopes were molybdenum-98 and molybdenum-95. Now I know this is biology class, but in chemistry, isotopes are atoms of the same element that have a different number of neutrons, which makes the isotopes have different masses. So molybdenum-98 obviously has a higher mass than molybdenum-95. When the ocean becomes oxygenated, molybdenum-95 is soaked into the seabed, leaving primarily molybdenum-98 in the water, which makes the water heavier. When the ocean becomes deoxygenized, molybdenum-98 is soaked into the seabed, leaving molybdenum-95, and this lighter isotope makes the water lighter. So using deposited rocks in the ocean, called shales, scientists were able to tell when water was heavier and when water was lighter, therefore when it was oxygenized and when it was deoxygenized. Knowing this information, we assume that the oxygen levels in the ocean reflected the oxygen levels in the atmosphere. Now Will is here to tell us how this oxygen got into our atmosphere.
The Second Devonian event was the largest oxygenation event in all Earth's history. It was also during the mid-Paleozoic. Vascular plants started appearing around this time, and their radiation sped up land erosion and sedimentation, and also the hydrological process, which is the exchange rate in between groundwater and the atmosphere. The plants on Earth's surface change carbon dioxide to oxygen through photosynthesis, and it is transported to the atmosphere by the process explained on the previous slide, the hydrological process. Since there was much more plant life on land, the organic carbon entering the ground increased continuously. This, in turn, adds to the oxygen entering the atmosphere and creates a buffer in which the oxygen is constantly entering the atmosphere because of the buildup of terrestrial carbon. And here is John with the take-home point for this presentation.
The take-home point is that vascular plants had a direct role in the rise and sustainability in the oxygenation of the atmosphere, and therefore the evolution of the Earth. Again, they help to speed up sedimentation forming in the hydrological process, and of course continues to sustain oxygen levels through photosynthesis. Vascular plants are responsible for all the evolution of living things we know today.